see here we have test 1, 2, 3, 4. We start at the beginning and then we shift it all the time. So the first character is the one which is most shifted actually, and all the characters are like this. And we have the XOR of all the characters in this checksum. So somewhere in the beginning of the file we have 2B72. If we open our hex editor, we should see that, or small r and plus in ASCII in the file at some place at the beginning of the file. Now this is great because this is somehow a check function, but this is not a cryptographic check function, right? This is a check function that they invented on the night when drinking some coffee and trying to find out how to fix the problem. They came up with this idea. And if you look at it a little bit, you can find out that, for example, we know immediately the length of the password. It should be, since we have a 1 here, there should be at least 7 characters in the password. There could have been a 1 here if this was a 1 also, but it can't be less than 7 characters because there would not be a 1 here. So this is a first hint. That's already useful. But then what is even more useful is we know that the last character has a 0 bit at the end. So this is an even character. So if you want to brute force, we will only use even characters here. And if we choose an even character like 4, we can then see that the next one must be an odd character because we have a 1 here, we have a 0 here, so there must be a 1 here too. So from each of the characters of the password, we know 1 bit. So we just reduce the size of the characters by half. We have half the character set from all the possibilities. And what is even more useful is that once you've chosen 1 for all those characters, for the last one, you don't even have to choose any random character. You can just calculate it. If you have chosen all of these, you can just calculate by XORing with the checksum what the last character should do. So what we saved here is we reduced the character set by 2, and we removed 1 character from the password. And depending on the character set, this can be much, much faster. And then additionally, this is just some shift and XOR operation. This has nothing to do with the initialization of Blowfish. So we don't do any Blowfish, we just do this type of operations. So let us see, so this is what I just explained to you. What the simple attack would be is to generate many, many passwords and to check every time if they have the corresponding checksum. If the checksum is wrong, we know there's no need to go through the whole Blowfish stuff because the password is wrong anyway. And this is what we did first. We took some large dictionaries. We knew where the software was coming from. This was not the German version. So we took some dictionaries of that language, and we found out of our thousands of words, there were 2 words which matched the checksum. And we said, well, maybe this is it. So we typed this word into the software, and then the software just crashed. It didn't show any message or anything, it just died. Because you can understand, it checked the checksum, it says, oh yes, it must be the correct password, so let's go decrypt everything. Oh, there's a pointer who says it's all the way there. Let me fetch that memory or whatever, and then it just crashes. So this is not enough, right? So once you have a candidate with the correct checksum, you still have to do the decryption with Blowfish and verify that the 2 first integers are small numbers, are close to 0. So that's the other attack. If you wanted to do it more efficient, you create a program which only generates passwords which have the correct checksum. So you never ever have to try to do something if the checksum is wrong, but you brute force through all combinations which have the correct checksum. So the way you do that, if we go back to the last slide, you know that for the last character, you have to choose an even character, so you choose for the last one only the even ones, so there's only half of the character set, and then you check for the next one the even or the odd ones, depending on the next bit of the checksum and so on, and in the end you can calculate the last one. I have an example here. I don't want to go into all the details, but you get the idea. We have already chosen the 5, where is my pointer, the 5 first characters, so now we are at the last 3 characters. So for I2, for half of the character set size, depending on one of the bits of the checksum, we choose the characters from one set or from the other set, and for each of the ones we have chosen, then we can add them to the checksum and try the last but 1 character. It's the same thing. We look at another bit of the checksum to define if it's from the even or the odd characters. It's not very readable, I'm sorry, but I didn't have that in idea when I wrote the code. I didn't think I had to show it to so many people, but then you get the idea. In the end, the last character of the password you can just calculate from the checksum. Then this gives you just some character which is necessary for making the checksum correct. In this case, we were looking for low alphanumerical password, so we knew it has to be larger than 96. If not, then this is not within the case that we are looking for. And then if we also have this condition, then only we do this Blowfish initialization. And we try to see if the result, here we have the initialization vectors, if they are really 0, 1, 2, 3, 4, 5. And this is where there is some information which we don't know, it's a small number, so we mask it out. And then we should have 8, 9, A, B, C, D. On the second integer, if there's 3 zeros also there. And if we have all those combinations, then most probably we have found the password, and we print it out, and then we can type it in, and in that case it worked. So the result is that we can now break it much faster because, as I told you, Blowfish was designed in a way that it was very slow to set up the key. When it's set up, it can encrypt very quickly, but to prevent brute forcing attacks, the key setup is very slow. So you get about 25,000 brute force trials or encryptions per second if you do it on a normal processor core. So it could be took a very long time to crack, for example, a 9-character alphanumerical password. With our method, if you have this checksum and you only try the ones which have the correct checksum, it would be 15 times faster. So if it's like 1 week and 15,000 weeks, you see the difference. In our case, we just did a test run with some very simple passwords, which were only lowercase alphanumerical, and we had the luck that this was the case. So we had a 9-character password made of lower letters and no numbers, actually. It took us 2.5 hours to break it instead of 1.7 years. Of course, the 2.5 hours came after 5 or 6 days of work, right? You try to find the thing, and then you program it, and then it takes 2.5 hours to break it. So sometimes it's worth spending the effort of understanding how it works before you just use the brute force, right? Okay, so let us see. Well, now it's open. We've seen the routine. We let it run. So it shows you all the different files that you have in there. There's no file in this one. See, it has a folder for all your different things. There must be a dragon hidden in this example also. It's here. You can store your passwords also using this Databecker private safe. And here they are. If you bearbeiten the things, it tells you, here they are, dragons. So that's your password. Okay, so this was the third demo. So what do we learn from that? We should come to a conclusion now of the talk and say, well, from looking at all of it, we can learn very interesting things. We can have fun. I think this is the first thing. There's not much more that we can, we can make a quiz. Oh, I'm sorry, I forgot about that. There's a quiz. So you saw all these strange cryptographic functions that we saw. We've reverse engineered, we understand how they work. And all of them have a same flaw that I did not mention. I tried to not mention that flaw or not in details, that you could also use to try to accelerate breaking of the system. So do me a favor, remember what that is. Anybody? Rainbow tables, yes, thank you very much. So there we go. None of them uses salt or an initialization vector. We saw the very first one. The first one was this MXI. This just did just a SHA-1 hash without any salt. You can find free rainbow tables on the internet to break that quite quickly. The second one was this one. This has a specific function. It does a write. The initialization vector is the write hash of your password, so it's not random either. But you can't find a rainbow table that does that already on the internet, but you can build one. You can spend some time creating that rainbow table and then breaking it. And you could create also a rainbow table for Blowfish, for the one we saw in the last example for Databecker, because in that case also there was an initialization vector, but it was always the same 0, 1, 2, 3, 4, 5, 6. A, B, C, D, E, F. So in all the cases, we could have used rainbow tables to break the system, but we would have to produce them first before we can use them, right? Okay, so what can we conclude from all of that? Cryptography is hard to implement correctly. You all knew that, right? This is nothing very new. But still, we find it again and again when you look at different softwares. This was all done last year. We had to look at 4 systems, and 3 of them are the one I'm presenting here. The last one was okay, so we see it's astonishing how many of those systems are actually not well made. So if you don't have the source code, the only way to know if your data is well protected